In this video, we'll talk about superposition of waves. Now, the meaning of superposition is that, so let's say in one region there are two waves. They propagate to the same region. Then their vibrations of media particles will add up. Let's look at the mathematical equation. So let's say we have one wave called y1 given by a1 sine kx plus minus omega t. Let's say k1 omega 1 and then plus phi 1, okay? And then second wave is y2 equals this a2 sine k2x plus minus omega 2t plus phi 2, okay? So they propagate to the same region, and then we'll think about how to add up these two waves so that we get a total displacement for media particle. It's given by yxt equals y1 xt plus y2 xt. And if you do that, so mathematically, we simply just add up these two equations, a1 sine k1x omega 1t plus phi 1 plus a2 sine k2x plus minus omega 2t plus phi 2. Okay, now in principle, the summation here, the result can be quite random, meaning there's no certain pattern that we can expect from this summation if there's no relation between these two waves. So that's why we're going to focus on some special conditions that can give us very nice summation from these two equations. So we're going to think about the in-phase wave sources. By in-phase, we mean the wave number k1 is equal to k2, okay, and angular frequency omega 1 equals omega 2. We also set the initial phases the same for both of them. And then, of course, we also want to use the same amplitude for the two waves so that we can either completely cancel the two waves if they oscillate in opposite directions, or add up the two waves oscillations if they point in the same direction for their oscillations. So that's the case we're going to discuss here, and then that's our conditions for the two waves, which we call in-phase wave sources. Okay, now under these conditions, you can say, doesn't that these two waves, they look exactly the same? So that's some catch here. So we know, let's say here is one wave source that's called S1, and here's another one, S2, and they are in phase. But if you pick, let's say, a spatial point at this location, then the distance from S1 and also from S2, they're different. We call these R1 and R2 to represent that distance to the same spatial point. And we're thinking about the displacement for this point at instant t. Now, if I think about that, and then I write down the equation that we had earlier from this page, then I'm going to get y1 due to source 1 is given by a sine k. X1 now is replaced by R1. So if you look around along this direction, along this R1 direction, then we essentially have a one-dimensional wave propagating in this way. And if I look along the R2 direction, then we essentially have another wave with the same speed propagating in this way, in this direction. So the x in the previous expression should be replaced by this r here. So I shouldn't, let me get rid of this x here. I shouldn't call this x anymore. I should call this r at a spatial point r. And then also here, there's r. And then this r will be by putting a coordinate system for the whole system, then we have a r measurement. But R1 and R2, they are different from r. Okay, so now R1 here give us the propagated distance from the source 1. So that's why we plug in kr1. And because of the propagation is this to the right side direction, so we're going to use negative sign here. Okay, the source is on the left side, minus omega t, and t here will be the same t. It's the same t for both sources. So I use the same symbol t here without labeling the index. And that's it. Okay. And y2 is given by a sine kr2 minus omega t. Okay, and the summation of them now is given by y1 plus y2 equals a, and then the two sine function. Two sine function summation. Okay, so now let's define two kind of result from this summation. So if the direction of the first wave oscillation is always in the same direction as the second wave, they will add up. They always add up. Then that kind of oscillation is called constructive. If that's constructive, summation we call the interference. That means that y1 and y2, they're always in the same direction. Their oscillations are always in the same direction. So let's think about how can this happen. So I'm going to draw first a sine function, and then we can use that figure to give us some equation that can always give rise to such a situation. Y1 and y2 are always in the same direction. So what kind of condition can give us that? So we're going to think about let's say sine as a function, let's say theta, okay, it's function of theta angle. And we know sine function look like this. Okay, so now if I think about 2 points, let's say this point and that point, 2 points that is lambda away. Sorry, in this case here it's not lambda, it's 2 pi away. 2 pi away. Then their motions are exactly the same. So they either have the same positive sign, same value, and or they have the same negative sign and same value. Okay. And if the distance between the 2 points, let's say this point and the third point here, then it's like distance 4 pi away. Then these 2 points, they have exactly the same kind of motion. They're either both positive or both negative and have exactly the same value. So that's why I want to say that if the two sine functions, their arguments here, this argument, their argument, they differ by an integer number times 2 pi. So let's write out this condition. So if kr1 minus kr2, this whole argument here is an integer number times 2 pi, then y1 and y2 always have the same sign and same value. They always add up. So that is the condition for the constructive interference. Okay, so omega t cancel out. So let's see what we have here. So k and then r1 minus r2 equals n times 2 pi. Okay, so n here, remember, is integer, so either 0 or plus minus 1, plus minus 2, etc. It could be any value, any integer value. So that gives us the condition. And usually in a picture, we see R1 and R2 value in terms of a distance, right? So that's why we want to kind of change this condition to talking about delta R here. What kind of condition should we satisfy for delta R so that we can have constructive interference? So let's move K to the right side. Now remember, the wave number K's definition is 2 pi over lambda, right? So 2 pi over K is actually lambda. So for n times lambda, n equals 0, plus minus 1, plus minus 2, etc. So that means that the condition for constructive interference is that the path difference which is defined as delta R equals R1 minus R2 or R2 minus R1, doesn't matter the order. The path difference is integer number integer multiples of wavelength lambda. Then we have constructive interference. Okay, so that's this condition. Now, what kind of condition give us destructive? When that's destructive, interference. Now, for the two waves to be destructive to each other, we need to have y1 and y2 they always in the opposite direction. Now let's still use the previous picture as an illustration. So let's say I'm looking at, let's see, this point here. And then another point I'm going to pick is this one. Let's see, that's one wavelength. Yeah, it should be here. Now these 2 points at this instant, this point is positive, this point is negative, and they have the same magnitude. And when we add up these 2 points, they will cancel out. Now at another instant, let's say this point goes down, then that point will go up. They will cancel again. And the condition for that is that this distance, the distance between these 2 points is pi. Okay, it's pi distance in in units of theta, if measured by theta. Now another point that can be destructive to the first point here is, let's see, should be this one. Let's see. No. Should be this point. Okay. And then the distance between them is this pi plus 2 pi, right? So we have 3 pi distance from the first point. And we can summarize the condition here. So we need a kr1 minus omega t minus kr2 minus omega t equals pi, 3 pi, 5 pi, etc. So it's half integer times 2 pi. So let's check that. So let's say when n equals 0, we get pi. When n equals 1, we get 3 pi. Yeah, that's right. And then n can also be negative. So when n equals -1, we get negative pi, etc. So n here is, again, 0 plus minus 1 plus minus 2, etc. Any integer. Now with that condition, we can do the same kind of rearrangement of the terms, and then the path difference delta r when n equals half integer times the wavelength times n times lambda, right? So the path difference is half integer multiples of lambda. Okay, by half integer we mean an integer plus 1/2, and that's called half integer. All right, so let's summarize the condition for constructive and destructive interferences. For constructive, we should have path difference equals integer times wavelength, and for destructive, we have the path difference equals half integer times lambda. Okay, so let's summarize what we talked about in the previous picture. So that's the superposition of 2 waves, and we're looking at the special case of in-phase sources and that superposition of the waves can be either constructive or destructive at certain points in the space. And we found out the relation for that to happen. Okay, so let's talk about the one-dimensional wave. Let's focus on one-dimensional wave. Superposition. And we're going to use this superposition to talk about standing wave. Now, to talk about 1D wave superposition, we have several questions. The first one is how to generate two in-phase wave sources. It's first question. Now, second question, what kind of conditions should we satisfy, just like when we talk about in general, constructive, destructive interference? So what kind of conditions should we satisfy to get constructive and destructive wave pattern? And these constructive destructive wave patterns, they appear in a standing wave, in a special wave called a standing wave. That's opposite to the traveling wave, so they're not moving, meaning these kind of wave, they're not moving. They're kind of like stationary in a space that you can see directly. So let's answer the first question first, how to generate two in-phase wave sources. Okay, so we're going to use the string as an example. String wave. Now here's the string. And suppose that we pull it tight with some tension force T, and then we also know the linear mass density mu, then we know the wave speed is given by square root of T over mu. Okay, so that's first, we understand that. So there can be a wave. So let's say we plug the string on one end, and then that will generate a wave to propagate in this direction. So let's say we do the source here, and then the wave propagate to the right. Okay. Now let's say we have finite length. Let's say the total length here for the string is L. And when the wave propagate to the right, you'll meet this end, the other end, and then it will be reflected back, right? Reflected back. So that's called the reflection. Reflection of the wave. And the reflection of wave has two properties. If the other end of the string, if it's fixed, end, then the reflected wave differs from the previous wave by pi phase. It's due to fixed end. And in another situation, if the other end here is open, it's not fixed. So let's say if we have a pole here, and then there's a ring connect to the string, and the string here can move up and down freely. Now in that case, it's called free end. Then when the wave is reflected back, it has no phase change. So that's a zero phase. difference, meaning there's no difference. So that gives us the idea that we can use either first case or second case to generate a second wave. When it's reflected back, it's going to go, let me use different color here, it's going to go back like this. So that's the reflected wave. And it should have the same wave speed because it's propagating along the same string. But now there's a pi phase shift, meaning whenever you have a wave for the previous wave that is upward, and then it's downward, the oscillation is downward. Okay. Now for the other one, for the free end, the reflected wave will have still have the same shape as the other one, because that's the zero phase change. So it's going to go back to and also follow the previous wave, retrace that path. Okay, so this one is less interesting. We needed something different here to create some kind of pattern, which we call standing wave. So that's why let's focus on this one. Focus on the fixed end wave reflection. And then there we have two phases that differs by a pi phase difference. And an interesting thing can come from there. So let's see. We're still talking about 1D superposition. So we have a string here that has length L, and we have both ends fixed. Now one end here is like a wave source generates a wave propagating to the right with speed v, wave speed v, and then when it's reflected back, so I'm going to use a different color here to represent a kind of reflection. So that's the wave traveling originally along this direction and then reflected back, going back. Okay, and that's the wave number 2. That's y2. Let's call it y2. And the previous one, let's say waves propagating from the source directly along this direction. Let's call this wave 1, y1. And when I join them here, they meet up here at this location. I'll put a dash down here. So they meet up here. So we want to do the superposition of the two waves right at this location. Now to set up the coordinate system, I want to say the origin O is at the first wave source, and x-axis point to the right. Now this position here, when they meet, we call it x. Okay, so that's relative to the origin O. It's x. Okay, so I can write down the wave number 1 is given by a sine kx, okay, because it travels a distance x to arrive at this location. So it's kx minus omega t, okay, like that. And then y2, I try to think about y2's expression. Now the distance traveled by y2 when it arrives at this location x is the total distance L traveled, and then it go back, right? The distance L minus x. So this portion here is L minus x, and the previous path before you arrive at the end, the other end is L. So that's why the total distance traveled here is L plus L minus X. Okay, so that's the total distance traveled or propagated by the wave. And then we still have the same omega t here, and then additional phase pi. Remember, this n is fixed, and as we discussed earlier, there's a pi phase shift. And then let's see what kind of equation we have here for y2. A sine k times 2l minus k times x minus omega t plus pi. So first, let's see, we have pi factor here. So think about, let's get rid of this pi. And we remember that the sine, let's say, pi minus theta equals sine theta, right? So that's just one identity from trig functions. And let's do that. So I want to use this pi here to subtract something without changing the equation here. So to do that, I want to put in this parenthesis kx and then plus omega t. And then there's some additional factor. Actually, let me put that additional factor also inside this equation, this parenthesis. Okay, so now according to that formula, then we have a sine kx plus omega t minus k times 2l. Okay, so now the purpose here is to get one wave that look like the previous one, the second wave to be look exactly the same like the first one, except that the propagation is the opposite direction. So now we know the negative sign means that the wave here is right moving. The wave here is right moving. And if I have a positive sign here, then that means the wave is left moving. So they move toward each other and then they superimpose to give us the standing wave that we need. And for that to happen, I want to make this term here multiples of 2 pi. So how about k times 2l is an integer times 2 pi. If I have that, then I can simply drop the last term, and we get a pure left moving term, left moving wave without any additional term, additional phase, because that additional phase could mess up the superposition, and then we'll simply just get some random patterns which we don't want. And in order to get the standing wave, so I want to say that here is the condition for getting a standing wave. So that's why I want to set up the equation that look like this. Okay. Now with that, we can see k, remember, is 2 pi over lambda times 2l equals n times 2 pi. So we can have some cancellation here of 2 pi, 2 pi. So the length of the string equals n times lambda over 2. Okay, so we should have a relation between the wavelength lambda and the total string length. They need to satisfy that the string length is integer multiples of the half wavelength. So that's our condition for generating a standing wave on the string. Okay, so let's keep that in mind. And then later on, we'll revisit this relation here. Okay, so now to summarize, we have the summation of these two waves, y1 and y2, and y1 is right moving, and y2 is left moving. Okay, and then we meet up at a certain location x. And then let's see what kind of superposition we get here. Now to sum up these two expressions, sine plus sine, let's recall another identity in trig functions. So sine theta 1 plus sine theta 2 equals twice sine theta 1 plus theta 2 over 2, and then times cosine theta 1 minus theta 2 over 2. Okay, so let's use that. So we have a here, a common factor, and then that's additional 2. So that's this 2a and sine kx minus omega t plus kx plus omega t. So omega t cancel out, and we have 2kx divided by 2. We have just the kx. For the cosine part, we have the difference between the kx cancel out when we do the subtraction, and we get 2 omega t divided by 2, we get omega t. Okay, so now you can see we have a separation of space and time contributions. And let's focus on the spatial contribution, and let's call this coefficient and ax, and then times cosine omega t. Okay, so now you can see for every point in the space, ax will be different. They have different values depending on their x, and for some special places, ax is maximum, meaning sine kx equals 1. Okay, so let's start a new page here. So let's look at the spatial contribution. To the superposition. So we have ax. So that's a spatially dependent amplitude, which is 2 sine kx, 2a sine kx. And let's talk about for some places where we have sine kx equals 1, then we have at these locations maximum amplitude equals 2a. Okay, so that's like the double the value of the single wave. Okay, now the solution to sine kx equals 1 is given by kx equals, so think about sine function. Let's say sine theta look like this. So we need to figure out all these points where we have sine theta equals 1, right? All these points. And that is given by, the first one is pi over 2. The next one is pi over 2 plus 2 pi. So we have pi over 2 plus integer number times 2 pi. And because we're considering, according to our coordinate system, positive x, so n equals 0, 1, 2, 3, etc. Now these positions are called, if I solve for x here, I get xn. These positions are called antinodes, okay, meaning the maximum amplitude position. Now another special places are sine kx equals 0. And they give us minimum amplitude, which is 0, meaning there's no vibration. At these locations at any time. And to get that sine kx equals 0, let's look at the diagram again. We need to have kx equals this, that, or this, or that. Okay, all these values. And all these values, they are given by n times pi, where n equals 0, 1, 2, 3, etc. Again, we're considering just the positive x. So xn equals n pi over k. Now let's do something more here. Let's say we know k is 2 pi over lambda. Okay, so if I replace k by that, then I cancel out this pi and this pi here. And then n go to the top, so we get n times lambda over 2. Okay, so we now we figure out all those positions, and at these positions, we have nodes, so-called nodes, meaning that there's no vibrations at these special places, and these special places are given by half wavelength times an integer. So it's integer multiples of lambda over 2, half wavelengths. So you can figure out those positions by measuring half wavelengths, multiples of integer multiples of half wavelengths from the origin. And let's draw that situation here. So here's the string starting from 0 here. Then we could have some half wavelength shape. So to ensure I have half wavelengths, I like to draw this kind of picture. So the length here is half wavelength for this shape, and we have another half wavelength, and another one, another half wavelength. Okay, and also remember we were talking about fixed ends. So the first point, the leftmost point, must be a node because it's fixed, so it cannot vibrate. And also right end here must also be a node. So we have fixed ends. That's why we have that. But we could have different situations. Let's say the right end, let's say is here, then that's also possible. Right end is here or there. So that's why we have different orders of standing waves. And let's talk about standing wave. Orders. Now the first order, which is also called a fundamental mode, is given by this shape. And the 2 points here, they are the two ends. Okay, so the length of the string should be L, and L should be lambda over 2, half wavelength. Now from there, we can say for the fundamental mode, lambda here is called lambda 1. Lambda 1 is given by 2L. Okay. Now if we know further the wave speed, let's say V, which in the string wave case is tension T over mu. Okay, suppose we know that, then we know V equals lambda times F, and that applies to any order of standing wave. So let's call it lambda n Fn. Now from here, then we can say the frequency F1 equals V over lambda 1 equals V over 2L. Okay, so that's the fundamental frequency. Now for the second order, we should have two such structures. So the length of the string must be this length from one end to the other. So L equals, now we call that 2 times lambda over 2. Okay, actually let's label all the orders. So that's lambda 2. So lambda 2 equals L. Now from there, we can say F2 equals V over L. And that's the second order standing wave. Now the third order be like this. And the length of the string is from one end to the other. Therefore, we have L equals 3 such structure, lambda 3 over 2. So lambda 3 is 2L over 3. And we have F3 equals V over 2L, and then there's a factor 3 here. Okay. Now we can kind of generalize this situation to the nth order, where we have L equals n times lambda n over 2. So lambda n equals 2L over n. And the frequency Fn equals V over lambda n. So that's n times V over 2L. Okay, so now we can see we can simply just multiply the nth order with V over 2L, which is the frequency of the fundamental mode. So you can say n times F1, simply just that. And in terms of lambda here, lambda 1 equals 2L, and then so we have lambda 1 over n. So for the nth order wavelength, it satisfies lambda 1 divided by n. Okay, so these are the wavelengths and also the frequencies of different orders of standing wave. And that's how you count the orders. Okay, so that's all for this video, and next time we'll talk more about the standing wave, how to count other situations of standing wave, especially for the sound wave. Okay, and that's all for this video. Thanks for watching. In this video, we will continue our discussion of the standing waves. And remember previously we talked about the string system, right? So that's the string instruments. And we know how to count the standing wave orders. So now today, let's talk about pipe instruments. And the system looked like this. So that's a pipe, and usually there's air inside. And then we're going to talk about different situations. Okay, so that's how to count standing waves in a pipe instrument. And for the pipe instrument, we can have different kind of situations. Let's talk first about the open pipe. Okay, now the picture looked like this. So both ends are open to the air, to the outside air. Okay, and the length of the pipe is L. Okay, and then just like before, we could have two kinds of situation here. We can use the displacement yxt of these air particles, and then we could write down y1 plus y2 of the two sound waves inside the pipe. They superimpose, and then we think about the boundary condition here. Okay, the boundary condition. So the boundary condition here is that before we talk about this, actually one more thing here. So remember the for sound wave, there are two kind of wave equation we can write down. One is using the displacement. That's the yxt that we talked about earlier. And the other wave equation we can write down is using the pressure, where we have pressure as function of position and time. Two descriptions. So now the boundary condition is very important. If the pipe both ends are open, that means that the air inside is connected to the air outside through this boundary, and at the boundary they should be continuous in the pressure. So for open boundary, the pressure inside the pipe equals the pressure outside. And because the pressure outside is a constant value, that means that they must be zero here. So the pressure inside at the boundary should be equal to 0 here. That means that it's node of pressure. Now remember, the relation between P and Y is that P is given by negative B partial Y partial X. Okay. Now by doing that, if y is a cosine function, then it turns into a sine function for p. If y is a sine function, then it turns into a cosine function for p. But in either case, if p equals 0 here for a node, then y must be 1, which must be an antinode. It's an antinode of displacement. So that's the open boundary condition. From there, we can say this n is p pressure node or y antinode. Okay, so now the same can be said about the other end, which is also open, which means that it's also p node or y antinode. And then later on, we'll talk about using these two boundary conditions. We can draw different orders of standing wave inside a pipe. Okay, but that's for later. Right now, let's think about closed boundary. What do we mean by closed boundary, and what's the implication for the pressure and displacement? Okay, now an example look like this. So let's say we put a cap on both ends, then that's closed, and that's closed. Now for closed pipe, we know the sound wave is a longitudinal wave, so the particles will try to like vibrate along this direction, and their propagation direction is also this way. Okay, so that's the longitudinal wave. But at the boundary, think about a boundary particle. A particle here cannot vibrate because it's blocked. The particle here will just stick to the wall, to the cap, without doing any motion. So that's why it's the closed boundary here is the node of displacement, which again, according to this relation between pressure and displacement, is the antinode of pressure. Okay, so that's an important condition we can use later on to talk about the standing wave orders. Okay, so let's start right away with the open pipe. Now here's the diagram. Both ends are open. And we also want to build a coordinate system so that origin O is sitting on one end, and the other end here is at L. That's the length of the pipe. Okay. So now the first order standing wave is given by remember both ends are open, so it should be Y antinode at both ends. So I still pick Y, the displacement, to discuss the standing wave. But before I do that, let's draw a diagram. So now if I have a sine function, then I have a shape that looks like this. Okay, so you want to have a antinode, so you want to pick this point here, right, to fit into one end, and the other end would be the other end, the other antinode, and that means that our origin O should be here, the left end of the pipe should be here, and the other end, the right end, must be it could be here actually, or there. So the first possibility is here. That's the right end, number one possibility. And number two, the second order would be here. Right end is fit here. Okay. Now this distance is lambda over 2, and the second distance is lambda. Okay, the total wavelength. So that's why we have the first order standing wave, where we have length of the pipe equals lambda 1 over 2, or lambda 1 is 2L. Okay, and then let's say we know the speed of sound is 340 meters per second at room temperature, and that equals lambda n times Fn as before. Then we have F1 equals V over lambda 1 equals V over 2L. That's the, again, fundamental mode. Now second order, L equals, now we have lambda here, a total lambda, so it's lambda 2, or you can say lambda 2 is L, F2 equals V over L. And nth order, L equals n times lambda n over 2, or lambda n equals 2L over n. Frequency is n times V over 2L, n times F1. So F1 equals V over 2L is the fundamental frequency. So all these orders, the length of the pipe satisfies exactly the same equation as in a string case. Now how about let's think about the same problem but with pressure. Instead of displacement, think about pressure here. So that's the pressure node, and also pressure node on the right side. So now if I think about the sine function again, the left end should fit here because that's a node for the pressure. And then the other end here should be, could be here, right? This first possibility is here, and second possibility, third possibility. So that's the first order, second order, third order. And that give us the relation between the length of the pipe. Let's say n equals 1, first order. So L equals lambda 1 over 2. Then we get lambda 1 equals 2L. Now second order, L equals 2 times lambda 2 over 2. So lambda 2 equals L. Now nth order, L equals n times lambda n over 2. So lambda n equals n times, sorry, two L over n, okay? And then correspondingly Fn equals n times V over 2L. So that look exactly the same as the previous nth order. So that doesn't make a difference. So you can use either the displacement or the pressure to talk about the standing waves. They should give you the same equations. All right, so let's mention the closed pipe quickly, okay? Now here's the pipe, the length is L, both ends are closed, and that means that their Y node on both ends, or you can say both ends are pressure antinode. Now according to that, you can do the same discussion as we did here, and then it turns out the equation looks exactly the same. So for the nth order standing wave, we have lambda n equals 2L over n, and frequency Fn equals n times V over 2L. Okay. All right, so let's talk about open closed pipe. Okay, now this should make some difference because here's the picture. So one end of the pipe is closed and the other end is open. Okay, so now that means that the left end here is displacement node, and the right end here is displacement anti-node. Or you can say the left end here is pressure anti-node, and the right end is pressure node. Okay, and you can use either one. You can use pressure or displacement. So let me pick the displacement here, and let's look at this sine function. Now I can fit to the left end. Let's say I'm thinking about y here. Okay, the left end is the y node, so that means that that's this one is okay. So that's left end, and right end should be displacement anti-node. So that should be this one, right? Or you can say that one, or the next one will be here. So the first order should give us the length of the pipe. So first order length of the pipe equals 1/4 of the wavelength, lambda 1. So lambda 1 is 4L. Okay, or you can say frequency F1 is V over 4L. Now second order standing wave is here, right? So we have the length of the pipe equals so that's like 3/4 of lambda 2. Okay, and then that gives us the lambda 2 here equals 4L over 3, and the frequency is 3 times V over 4L. Now the next order is here. Third order, L equals 5/4 lambda 3. So lambda 3 equals 4L over 5, and frequency equals 5 V over 4L. Okay, so now we can generalize the situation to, let's say, lambda nth order equals 4L over so I'm going to define n here as 1, 2, 3, etc. So to get to the first order, I need to do this n here should be that's like 1 here, right? So it's actually it's 2n plus 1. So I'm going to say n start from 0. And then for the first order, that refers to n equals 0. And then when I plug in 0 in this expression, I get 1. So I have this one here. So that's why it's 2n plus 1. And for the second order, I have n equals 1. And when I plug in here, I get 3. So that's why I have 3 here. For the third one, n equals 2, so I get 5 here. So that's why the lambda n here is representing n equals 0, 1, 2, 3, etc. And we have 4L over 2n plus 1. And the frequency Fn is 2n plus 1 times V over 4L. Okay, so again, n is 0, 1, 2, etc. Alright, so let's give you an example of how to count the standing waves in open-closed pipe. Okay, so now lastly, I want to talk about the energy. in a wave. So now let's see, here is the wave source. And let's say wave source has power P, okay? So it means that it emit the amount of P energy per second. Emits energy P per second. Okay, so that's the definition of power. And then you will emit in all directions. And let's think about the isotropic media. Means that in any direction, the propagation of the energy is uniformly. So that's why we can say, suppose there's a spherical surface that's radius r, and then we can think about the energy distribution on such a surface. So we're going to calculate energy per unit area. We call it I. Is total energy P divided by the total area of the spherical surface, which is 4 pi r squared. And that is the energy distribution we call it intensity. So it's power per unit area. It's defined this way. Now with this intensity, we can also apply it to the sound wave. And people try to measure the sound wave intensity, and then they use another unit called decibel. Decibels, that's like a unit for intensity. So how to define this? Because the hearing of human being, the intensity that human being can hear has a really large range. So it starts from the lowest intensity that people can hear is 1 times 10 to the negative 12 watt per square meters. So by the way, the unit here for intensity is watt per square meters. Okay, so that's the hearing threshold for human being. Human being can hear this small intensity and go up to some very large intensity, like order 1. So that's the huge order of magnitude that we need to cover. So that's why watt per square meter is not a proper unit. So decibel here is a proper unit. And let's define this decibel. Decibel is given by this formula. So that's a 10 decibel constant times a log function using 10 as the base. And we have intensity I over I naught. Okay, so every intensity need to be compared with the hearing threshold of human being. And that ratio need to be input into the log function, which is 10 as the base. And then we get the decibel. So let's say some example. So let's say we're thinking about, let's say 10 decibel. And think about what is that, okay? So if beta equals 10, then the intensity satisfies this equation. That means that I over I naught equals 10, right? So So I equals 10 times I naught. So that gives us 10 to the negative 11 watt per square meters. Okay. Now another example, let's say beta equals, let's say 100 decibel. And what is that? So let's see, we have 100 here for the left side. Then we have I over I naught equals 10 to the 10th. So the intensity is 10 to the 10th times 10 to the negative 12. So that's 10 to the negative 2 watt per square meters. Okay, so that's why the range of the intensity is really large for using unit watt per square meter. So that's why it's not as convenient as the decibel unit, where we have just a small range, some regular number that you can say. Okay, so that's all for this video. Thanks for watching.